For any angle in standard position, we can take a point that lies on the terminal arm of that angle, and then by going straight down, we can create a right angle with that x-axis. And then if this is the point, let's just use x and y for the x and the y coordinates. So whatever that x coordinate is, that's how many units over we're going on the x-axis. So that forms the base of my triangle, that x value. We know that whatever that y coordinate is, that's how many units we're going up on the y-axis. So that forms the height of the triangle. And then in terms of the hypotenuse of the triangle, this point on the arm, depending on where that terminal arm lies, so if we were to continue rotating that angle, you can see that we're going around here in a circle. So the distance from the origin to that point is the radius of that circle. And so we can actually calculate that value by knowing a point on the terminal arm. Because we have a right triangle, we can use Pythagoras' theorem. This would be the hypotenuse of that triangle. So we have x squared plus y squared equals r squared, and then square root to isolate r, and we can find the value of r in order to get the exact trigonometric ratio for that particular angle. So what we're now going to do is think of our sine, tangent, cosine, primary trig ratios in terms of the relationship between x, y, and r. So we know sine from this angle is opposite over hypotenuse, so we're going to have y over r. We know cosine from this angle is adjacent over hypotenuse, so that would be x over r. And we know tangent of this angle is going to be opposite over adjacent, so y over r. So these are kind of your new trig definitions that we can use for any point on a terminal arm in order to find those exact trig ratios. Because r is the radius of that circle, it's always going to have a positive value. X and Y, depending on what quadrant that terminal arm happens to lie, you'll have to check if we have a positive or a negative X and Y coordinate. So if we are asked to determine trigonometric ratios in exact form, that means you can't just put it in your calculator. That's going to give you an irrational number often. So we have a point 4, 2. So we can go ahead and plot that 1, 2, 3, 4, 1, 2. And we know that the terminal arm will pass through that point. So my angle of rotation is right here. That means that my x coordinate is 4. I'm going 4 units over on the x-axis. My y coordinate is 2. We're going 2 units up on the y-axis. I can see that we have a right triangle, and we can calculate the radius of that triangle using Pythagoras' theorem. So 4 squared is 16, plus 2 squared is 4 is the square root of 20. We can pull a 4 out of there, so we end up with 2 times the square root of 5. And we always want to simplify the radicals, so we now have the exact value for the hypotenuse of that triangle. Now, if we're going to do sine, we know sine of that angle is opposite over hypotenuse. So we have 2 over 2 root 5. And again, we do not want to leave a radical in the denominator, so we're going to rationalize. We're going to multiply by the square root of 5 over the square root of 5. Remember, this has a value of 1, so we're not changing the question. Multiply the numerators, and we have 2 times the square root of 5, and then 2 times 1 is 2, 5 times 5 is the square root of 25. That is a perfect square. That's the whole point in rationalizing. So we know we have 5 times 2 gives us 10, and then we cannot pull a perfect square out of this. Reduce. So we know that the sine of that angle is the square root of 5 over 5. Cosine of that angle. Now we've got adjacent over hypotenuse. So we have 4 over 2 times the square root of 5. And again, we're going to rationalize that denominator. And this will simplify down to 2 times the square root of 5 over 5. Tangent of this angle is opposite over adjacent. So 2 over 4 will reduce to 1/2. And we now have the 3 primary trig ratios in exact form. Our next point is -3, 7. So the first thing we're going to do is plot that point. So on the x-axis, we're going -1, -2, -3, and then we're going up 1, 2, 3, 4, 5, 6, 7. So that lies on the terminal arm. So we can draw in that terminal arm, and then the angle of rotation is going to be that one in purple. This here is my reference angle. So the first thing we're going to do is calculate the radius. So we're going to go -3 squared plus 7 squared, and then take the square root. There is no perfect square in 58, so we can leave that just as the square root of 58. And then from our reference angle, because we have to use the angle within that right triangle, we have opposite over hypotenuse. So 7 over the square root of 58, and again, we're rationalizing that. And so when we multiply the square root of 58 times the square root of 58, and then square root that, we will just just get 58. So we can kind of speed this process up a little bit. Cosine of this angle is adjacent, that -3 over the hypotenuse. And again, you're going to rationalize. And if you can see what's happening with the rationalization, I know I'm going to be multiplying by the square root of 58. So I'm going to have -3 times the square root of 58 in the numerator. And then I will just have 58 in the denominator. And then just check, is there a perfect square we can remove? In this case, there isn't. And then can we reduce those whole numbers? Tangent of this angle is opposite over adjacent. We don't want to leave a negative in the denominator, so just move it either out front or up into the numerator. We're going to do this 4 times. I want my terminal arm to lie in each of those 4 quadrants, and you'll see why in a sec, so just hang in there. Next thing, we have -3, -2. So -1, 2, 3 and -1, 2. So that point is going to lie in quadrant 3, and we can go ahead and draw the terminal arm. So my angle is rotating here. I'm going to use that reference angle to get those 3 primary ratios. So first thing we're going to do is get the radius, and then we're going to calculate those 3 ratios. And in our last one here, our point is 1, 2, 3, and then -1, -2, -3, -4. So then we can go ahead and draw that terminal arm. So I'm going to use this reference angle to get those ratios, and our radius, 3 squared is 9 plus -4 squared is 16. That gives us the square root of 25, which is a perfect square. So we have a whole number, which is nice because we won't have to rationalize anything. So sine of this angle, opposite over hypotenuse. Cosine of this angle, adjacent over hypotenuse. Tangent of this angle, opposite over adjacent. Okay, so here's what we want to notice now. If our terminal arm lies in quadrant 1, anywhere in this quadrant, x will be positive and y will be positive. And then take a look at our trig ratios. All of them are positive. If we have a terminal arm that lies in quadrant 2, so anywhere in here, we're going to have a negative x coordinate and we're going to have a positive y coordinate. If you look at these ratios, the only positive ratio is the sine ratio. Both cosine and tangent are negative. If we have a terminal arm that lies in quadrant 3, we have a negative x coordinate, we have a negative y coordinate. So everything in here will be negative and negative. Our 3 primary trig ratios, tangent is positive because a negative divided by a negative gives us a positive value. Sine will always be negative, cosine will always be negative. And if our terminal arm lies in quadrant 4, we will always have a positive x coordinate and a negative y coordinate. The cosine ratio will end up being positive. The other 2 will be negative. And one way that we can remember which trigonometric ratios are positive in which quadrants is what we call the cast rule. So if we start in quadrant 4 and then rotate counterclockwise, C-A-S-T spells cast, we know in quadrant 1 all of our trig ratios will be positive. So quadrant 2, only the sine ratio is positive. Quadrant 3, only the tan ratio is positive. Quadrant 4, the cosine ratio is positive. So in this example, we have to get the values of sine of theta and tangent of theta if we know that the cosine of theta is -3/4 in quadrant 3. So the first thing we always want to do is draw a sketch. So we know that the terminal arm will lie in quadrant 3. We also know, and I would just ignore the signs for a second, cosine is adjacent over hypotenuse. So from this angle in the right triangle, adjacent is right here, so I would just put a 3. Hypotenuse is right here, I would put a 4. Now, we know that we have a negative ratio. We also know that the hypotenuse cannot be negative. And you can even take a look at the axes. So we know that this is the negative x-axis, so that's a negative. We also know that we're going to have a negative y coordinate here. So we can again use Pythagoras' theorem to calculate that y. Now, this time 4 is the hypotenuse. So we have 4 squared, and then we're going to minus -3 squared. Take the square root of that, and that will give us the y coordinate. So we're using a squared plus b squared equals c squared. We're just rearranging that in order to isolate for what we want. And we can see that y is going to be the square root of 7. But if you look at the diagram, we are below that x-axis. So this is negative the square root of 7 right here. We can even put the negative sign in there. So we know that x has a value of -3, y has a value of negative the square root of 7, and we know that the radius is 4. So we can go back to those ratios that we developed at the beginning of this lesson, or you can just take a look visually. So I know sine of theta, sine is opposite over hypotenuse. So we can go ahead and fill that in here. And there's nothing we need to do to simplify. There is no perfect square in here, and we can't reduce those whole numbers. Tangent, we know from that angle, is opposite over adjacent. So in this case, we are going to have a negative divided by a negative, which will give us a positive value. So we now have those two ratios. And then just check to make sure that all of your signs are accurate. And then you can also check, so CAST, tangent is the only ratio that should be positive in this quadrant. Tangent is positive, sine is not, nor is cosine. So that also checks. And these are not drawn to scale, by the way. So what I would do here, so if we can see that we're given a ratio and our terminal arm lies in quadrant 4, I would just put a point somewhere in quadrant 4 and then draw in the terminal arm. We know we're going to create a right triangle, and we're going to use that reference angle in order to get some of these values. So we can go ahead and draw in our right triangle. And then if we take a look at this, we know that sine is opposite over hypotenuse. So again, just ignore the signs for a second. From this reference angle, this is my opposite. So we're going to put a 2 there, and then my hypotenuse is going to be here. Now I know the hypotenuse cannot be negative, so that means this is negative. And take a look at the diagram. This is the negative y-axis, so that's going to be a -2. And then we also know that this is a positive x-axis. So this will have a positive value for x, which we can calculate now using Pythagoras' theorem. Once we know the x, y, and r values, then we can calculate those trigonometric ratios. So this time we have the cosine of beta. So cosine, remember, is adjacent over hypotenuse. And then the tan of beta, opposite over adjacent. And again, rationalize to get that square root of 21 out of the denominator. And then check, is there a perfect square in here? And there isn't. And then can we reduce those whole numbers? We can't, so those are the ratios. And then we are terminating in quadrant 4 here. So this is cast. Cosine should be the only positive ratio. Cosine is positive. My other two are negative. In our next example, we're asked to determine the exact value for each angle, beginning with the sine of 225 degrees. So what I've highlighted in yellow is often what you'll see in a question. It's not necessarily going to say use the special triangles. The first thing we want to do is draw a sketch. So we're looking for that 225 degree angle. We're going to start here. We're going to rotate 90, 180, and 225 will have a terminal arm somewhere in quadrant 3. So we can just put that in there somewhere. And then the next thing we want to do is get that reference angle. So if we know that this is 180 degrees, we can take the 225, subtract 180, and we can see that this is 45 degrees. That tells me that I have an isosceles triangle, and I know that is a 1-to-1 ratio with that square root of 2 as the hypotenuse. Now, the next thing we're going to do is look at the signs. So I can see that this is the negative x-axis, this is the negative y-axis. So I'm going to actually put a -1 and a -1 on here. And remember, this could be -10, this could be -10. This just represents whatever this distance is. It's the same distance here, and then we can calculate that hypotenuse. Now, we need the sine ratio. So sine, if we start here, is going to be opposite divided by the hypotenuse. So we can go ahead and set that up, and then we cannot leave a radical in the denominator, so we're going to rationalize that. And the sine of 225 degrees is negative the square root of 2 divided by 2. And then just use your CAST rule to double check. So CAST, tangent is positive in quadrant 3, which means sine is going to be negative. So you can make sure that we have the right sign there. So in our calculator, if we were to enter the sine of 225, so go into mode and just make sure that you are in degree mode. So we can go down here, over here, and then press enter. And then just go second function quit to get out of that. So if we were to enter sine of 225, we're going to get this ratio. So we can see this is an irrational number. This is the exact value. So if we were to go negative the square root of 2, and then just right arrow to get out of there, and then we're going to divide that by 2, you can see they are equivalent. This, however, is exact, and we can use that reference triangle to generate that exact measure. So this is the ratio for any triangle with a 45-degree angle of the opposite side to the hypotenuse side, and the sign depends on which quadrant that terminal arm lies in. And then tangent of 330. So again, if we start here, we're going to go 90, 180, 270. I know 330 is going to have a terminal arm somewhere in quadrant 4. So we're going to get that drawn first of all. And then the next thing we're going to do is get this reference angle. So if this is 330 degrees, I'm 30 degrees short of that 360 full circle rotation. So that tells me I have a 30, 60, 90 triangle. And remember, across from that smallest angle is my smallest side, which is going to be 1. So we're going to ignore the signs for a second. This is a 1:2 ratio, which means that is the square root of 3, that measure there. And then take a look. So we can see this is the positive x-axis, but the negative y-axis. So I know that has a -1 there. And then we're looking in this particular case for the tangent. So from this angle, tangent is opposite over adjacent. So we're going to set up that ratio, and then we need to rationalize the denominator, and then make sure you check. So this is quadrant 4, cosine is positive, tangent is negative. And the last thing we're going to do in this lesson is take a look at a quadrantal angle, which is just an angle whose terminal arm lies on either the x-axis or the y-axis. So 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees, and so on. Let's say, for example, that we want to calculate the trigonometric ratios for 90 degrees. So we know 90 degrees is going to rotate to there. So the easiest way to do this is to choose a point on the terminal arm, and the easiest point to work with is 1. So I know that if I have a point here, the coordinates of that point are going to be 0, 1. And then if you remember those trigonometric ratios we defined at the start of this lesson using x, y, and r, we know that the sine ratio is just the opposite divided by the hypotenuse. Now in this case, we can see that the y-coordinate is 1, and the radius of that circle, so if you remember, as we rotate here, the radius in this case is just that 1 unit. We can even draw a circle over top here so that you can see, but if we have an angle in standard position, that means the center of the circle is going to lie at the origin. I've just laid it over top here, so we can see that from here to this point that we chose, if this point is 0, 1, that means from here to here we have a radius of 1 unit. Y is equal to r when we're right on this arm. So we can substitute in here 1 over 1 gives us a sine ratio of 1. The cosine ratio we know is adjacent divided by hypotenuse. My r is again that value of 1, so we can substitute that in. 0 divided by 1 is 0. And the tangent ratio, so tangent is opposite divided by adjacent, substitute those values in, but we cannot divide by 0. So in this case, it's undefined. There is no tangent ratio for a 90-degree angle. And then you can always verify these. So in your calculator, if you type in sine of 90, you should get a value of 1. If you type in cosine of 90, you'd get a value of 0. And tangent of 90, your calculator will say error, that does not exist. And we could try this again now for 180 degrees. So I know I'm rotating to here. So this is my terminal arm. Choose a point along that arm, and again, because 1 is the easiest to work with, I would choose right here is going to be now -1 and 0. We're not going up or down off that x-axis. And we can see that if we're working with this point, I have an x-coordinate, a y-coordinate, and my radius is still going to be +1. That's a distant measure. So our x-coordinate is -1, but we still have a radius of +1. So again, if you go back to your 3 ratios here, sine is y over r. So my y-coordinate is 0. There would be a radius of 1 unit, so 0 divided by 1 is 0. Cosine x divided by r, so our x-coordinate is -1. R is still that +1. -1 divided by +1, you have a -1 for a cosine ratio. And tangent y divided by x. So y is 0, x is -1, gives us a ratio of 0.